welcome Amit to give the talk today. I know the schedule originally had Ness scheduled to give us a talk, but the speaker emailed me Thursday evening last week saying that there's been a change of heart about how much they could share about their architecture, and they will be able to give a talk, but they need to figure this out. So hopefully at some point in the future that will happen. And Amit very, very graciously agreed to give this talk a week early. He's going to talk about something he's been doing on really bringing the internet to the Internet of Things.
To things, yeah. Thanks, Phil. So as Phil said, I'll be talking about Beetle, which is a system that we're building right now to provide sort of networking communication to Bluetooth Low Energy devices in the Internet of Things. Okay, so if you'll indulge me for a second, I want to philosophize and also use a bunch of buzzwords to kind of paint a picture of what I think we would all like for the ideal Internet of Things to look like. Okay, so in the Internet of Things, we will have all of these devices that are connected together. So devices in our home, on our person, devices that we might interact with casually in the environment, in our vehicles, and all those things will connect with each other, but also with services in the cloud and with our personal devices like our laptops and phones, etc. But it's not just that these things will be connected. I think that the ideal vision of the Internet of Things also allows us to build applications to sort of leverage this communication. Sorry. Okay, but that's not what the Internet of Things looks like today. Instead, it looks something like this. Right. So here we have the same things, and they're, in some sense, many of them are connected to some other things. But all that communication is sort of mediated through very specific applications. And I claim that this is not really an internet. Right? And why not? Well, instead of having sort of a rich sort of many-to-many communication architecture, we have very narrow, sort of vertically integrated stacks of applications where certain devices can connect to other devices through particular applications. And there are several reasons why this is the case. Some of it is not fundamental. Some of it is just that Nike wants us to use the Nike app to connect to their fitness band. But unfortunately, some of it has to do with sort of the constrained nature of how, in particular, Bluetooth Low Energy, how that communication architecture works. And so in this talk, I'm going to speak specifically about Bluetooth Low Energy and some of the constraints that create this problem. And then I'll talk about Beetle, which is a system that specifically is meant to address the constraints in Bluetooth Low Energy and enable sort of an internetwork despite those constraints. Okay, so first I'll talk a little bit about Bluetooth, the current Bluetooth Low Energy architecture, what the protocol looks like and how it's used currently by devices. And then I'll go on to Beetle. Okay, so Bluetooth Low Energy is a single hop protocol. It's a link protocol, right? Which means that it connects a single device to a single, typically gateway device, right? There's no notion of networking. The protocol specifies all three of the physical link and application layers. So it's sort of a full stack protocol. And it's particularly optimized for small exchanges of data at low energy. So for example, a typical exchange is about 24 bytes. Technically, at the application level, it can go larger than that, but that's not necessarily supported by most devices. So 24 is sort of a typical maximum payload that you can actually transfer. And these exchanges of data happen very infrequently. So the maximum you can do is about every 7.5 seconds. But in practice, most of these, most pairings of devices will exchange data, on the order of every hundreds of milliseconds or seconds. So very low bandwidth. But on the other hand, it's extremely power efficient. So on average, a typical application will consume something on the order of single-digit microamps.
At what voltage?
Sorry?
At what voltage?
3.3 is the one I know of, but and this means that these devices can run for years on something like 150 milliamp hour coin battery, which is pretty cool. Okay, so this is the Bluetooth Low Energy sort of protocol stack. At the bottom, we have the link layers. And on top of the link layer, there's sort of two types of interactions. One of them, on the left, are advertising packets. And the other are for packets that are for connected devices. I'm not really going to talk about advertising packet. No, I'm not going to talk about it at all. Not really. Because, well, for one, they're even more constrained. They're typically used basically to form connections or for very, very simple things like sort of notifying proximity. And it's very difficult to build sort of richer applications on top of this. So I'm going to focus on the protocols that are used inside of a connection between two devices. And so there's the link layer, and on top of that, there's oh, sorry, Baram, you have a question.
For the previous slide,
yeah.
What was the range effectively?
So the spec says, I think, about 100 meters, but I think in practice it's more like 10, 20, 30 meters. Obviously, it depends on the radio. Yeah.
On the slide, is it years if I just sporadically send packets, or that also includes typical computation?
So this is like a typical application, but a typical application is like not doing stuff most of the time. So something like a heart rate monitor isn't really. It's kind of every once in a while it'll wake up and measure the heart rate and then send a packet. So that kind of all happens in the same within this same little span of time. So all of it's kind of asleep most of the time.
So is it because the device typically breaks before you actually run out of power or gets replaced?
I mean, they often still have batteries, but they just last for a long time. Or was that the question?
I just meant the life cycle of these devices seems shorter than several years.
Oh, I see. I actually can't. I can't speak to that. I have not had any Bluetooth Low Energy devices for more than a year.
Mine all broke.
Yeah. Baram, you asked your question, right? Yes. Okay. So on top of the link layers, there's sort of two levels of the protocol. The first is L2 cap, which is logical something channel whatever. The point is that it gives an abstraction of logical channels on top of a single link. So I can sort of multiplex different channels of communication on the same link. And then GATT, generic attribute protocol, is the actual application level protocol that the devices typically use. Okay, so first, very briefly, what the link layer looks like. So it's the spec calls it a piconet topology. Basically, there's two types of roles in the Bluetooth link layer. There's the peripheral role, which is typically something like the heart rate monitor. It's the peripheral device, the small device that's power constrained. And then there's a central device like your smartphone or laptop or some gateway in your home. So centrals can manage connections with multiple peripheral devices simultaneously, but typically a peripheral can only connect to one central. There's a slight caveat, which I'll touch on for a second later, but it's basically true. Right, and so we sort of have this this topology where all the peripherals in a piconet are connecting to the same central, and they can't really communicate with each other outside of it. Okay, so on top of that link layer, like I said, we have these logical channels. And in the L2 cap layer, L2 cap provides a reliable transport in Bluetooth Low Energy. And it's a little bit different for regular Bluetooth, but on Bluetooth Low Energy, there's a reliable transport, meaning if I send a packet, either the connection will break eventually or I know that that packet has been sent. And importantly, some of the channels on L2 cap, so you can create arbitrary channels, but I think the first 5 channels are reserved. So L2 cap sort of is where applications manage things like flow control and also have sort of a reserved spot for the application protocol GATT. And that's going to be important for sort of being backwards compatible in Beetle. Okay, so finally, on top of L2 cap, we get the protocol that applications actually use. And this is a protocol called generic attribute protocol. And this is sort of a diagram of the abstraction that you get. GATT, I sort of think of it as a key type value store. So basically, every side of the connection can export a certain set of attributes. Each attribute has a handle which uniquely identifies it in that particular device. An attribute has a type which specifies what kind of thing the value inside of it is, and it has a value. And then further, these attributes are aggregated into things called characteristics and services. So a characteristic would be something like the current heart rate, and a service would be the heart rate monitor service. So a service might have several characteristics that are all related to each other. For example, the heart rate service also has, I think, a location characteristic which says where it is on the body.
What's the difference between handle and type?
So the handle is like a key. So it's just a number, and the type says the kind of thing that it is. So if the type is a service, right? So you can have multiple attributes of the same type, but only one attribute has the handle 0200. Does that make sense? And so typically you would use the type of the attribute to, for example, look up all the services on a device. There's a command that's like find by type, which gives you back all of the attributes that have a particular service, for example.
And it gives that back to you broken up over multiple 24-byte packets then?
It may or may not. Yeah, it may or may not. It may span multiple packets if, depending on the specific subcommand. You also give it a range. So typically, yeah. OK, so remember we had two roles in L2 cap, peripheral and central. GATT has two other roles which are sort of orthogonal to the L2 cap roles, or sorry, to the link layer roles. So there's a server, which is the device that hosts certain attributes, and a client which sort of consumes those attributes. And both peripherals and centrals can be both servers and clients simultaneously for different attributes. Right, and so as I said, it's a key type value store. And we have the kinds of operations that we might expect from a data structure like this. So we can read and write attributes. We can also get notifications when those attributes change, sort of asynchronously. And we can do search operations like find by type or find a particular range of attributes based on the handle. Yeah.
This is kind of a bit different than HTTP, where the asymmetry in the client and the server is reflected in the application level protocol.
So Phil pointed out that this is different from HTTP in that the asymmetry between client and server is also reflected at the application level protocol. Keith, do you have a retort?
No.
OK. I'm kidding. OK. So here's just a very, very simple example of the GATT protocol sort of in action. This is actually a typical use case. So over here on the left, we have a heart rate monitor. This is actually a heart rate monitor watch, but it's a prettier picture than the band that goes on your chest. And a client phone, probably some app that's connected to it that wants to show you the heart rate. And every second, the server is going to notify the client of whatever the current heart rate is. Make sense? OK. So some important and useful properties about GATT. It's designed for interoperability. So for example, the types of the types of attributes are standardized. So the name for the type service or the name for the type characteristic is sort of understood by all devices. And moreover, the organization of those services, so which characteristics a particular service has, and how they're formatted, et cetera, is also standardized. So the Bluetooth SIG sort of standardizes over a whole bunch of different profiles like heart rate and glucose level and cadence, et cetera. So sort of devices operating at this level is really nice if we care about devices interoperating with each other and being able to sort of consume services from different devices. It's also transactional, and by that I mean that we sort of for free, well, we pay a performance penalty, but it's in the protocol. We get ordering of packets, and we get that because you're basically not allowed to send a command packet before you've gotten a response for a previous one. So that's useful. It's also something that we're going to need to preserve when I talk about Beetle. And the third one is that it's quite a high-level protocol. But in fact, for embedded devices, it's typically the only protocol that application processors get access to. So in most of the Bluetooth chips that you can buy for embedded systems, you basically get to talk GATT, but you can't, for example, create your own L2 cap channels. So sort of the hardware or the firmware on the chip manages the lower layers for you. OK, so remember, a peripheral can only talk to a single, or sorry, can only maintain a single open connection to one central device. The asterisk there is that technically the protocol specification allows for more than one connection from a peripheral to centrals. But for one, it's still a limited amount. And second, typically that just doesn't, it's just not the case in most hardware. So most hardware only allows a single connection. OK, so the result of this is that we get one-to-one communication in practice between devices, and not only centrals, but applications on a central device. Right? So typically, if we have a bunch of devices connected to a central, an application, they'll only have one connection open to the central, and a single application will sort of own that connection. Right? So, so my heart rate monitor, for example, from the example before, is owned by a single app. And other apps basically can't access the connection to the heart rate monitor unless the app like explicitly, has some external interface for other applications. OK, so the result of all this is basically this vertically integrated applications that I talked about before, where because there's no network for the Bluetooth devices to connect to sort of broader things over the network, then applications on the gateway have to interpose on the actual data exchanges between devices and something else. So for example, if my heart rate monitor, if I want to store heart rate monitor data in a cloud server somewhere, I'm going to have to have an application that consumes that data, reads the actual heart rate data, and transforms it into something like a RESTful HTTP request or something over the internet. Right, so for example, if I have, so if I have a set of devices that I want to interact in a way that the applications that manage them don't support, well, tough luck. OK, so to sort of summarize the limitations that I've talked about for Bluetooth Low Energy, Bluetooth Low Energy is a link connection, not a network. And that means that currently it's not possible for peripherals to talk to each other. It's not possible for multiple applications to talk to the same peripheral at the same time. And peripheral to cloud communication is only possible if the application sort of mediates that exchange. And so the result is that we have this ecosystem of walled gardens, which is, of course, not what we want. And so for example, this is just a running example that I'm going to use for the rest of the talk. Of an interaction that we can't do right now. So here I have a heart rate monitor and some sort of fitness equipment like a treadmill, and of course my phone that's along with me, and there's some server in the cloud. And what I want is for the heart rate monitor and the treadmill to be able to interact, because let's say I want the treadmill to show me my current heart rate on a display. I also want to store some data. I also want my phone, an application on my phone, to keep track of my heart rate so it can store it for later, so I can view a graph, for example, of my heart rate across multiple exercises. Oh, sorry, question?
You cannot have a peripheral and a central in a device because it's too consumes too much power, or is it the manufacturer limitation?
Yeah, so you could presumably put two separate chips on the device. The central role should typically be much more power consumptive because, effectively you have to be on for longer. The radio has to be on for longer, and you're not allowed to sort of skip as many communications. So you can, Okay, so we have these two separate applications. One of them is going to, suppose, store data locally on my device and show me some graph at the end of my workout. Another one is going to send the data to some sort of social service like Strava that will let me compare my results with my friends. And finally, I want to log my heart rate also to some server, somewhere. What did I do? And the point is that this interaction is not possible, of course, unless there's one application on the phone that specifically enables this set of interactions. And the reason is that the current Bluetooth architecture doesn't allow us to sort of compose applications at all. Okay, so this brings us to Beetle, which is a system that we're building that enables networking for Bluetooth devices despite these constraints. And it does so using three mechanisms that I'll talk about. Okay, so what do I mean by a network? Well, specifically three things. The first is that we want peripherals to communicate with each other. So the heart rate monitor and the treadmill, even though they're both Bluetooth peripherals, should be able to exchange data. We want to allow multiple applications to safely access each peripheral so that I can have both my Nike graphing application as well as my Strava social whatever application. And finally, we want to allow peripherals to interact with the broader internet without necessarily having to be mediated by a particular application. So to achieve this, Beetle is a software layer that runs on the gateway device. So for example, your phone or your laptop. And it achieves this. It creates this network by exposing three mechanisms to the operating system and to connected devices. The first is called HAT, handle address translation, and that mechanism allows multiple peripherals to talk to each other. Virtual devices exposes Bluetooth to software on the phone and to remote services over the network in a safe way that allows them to share the same peripheral. And finally, service export control, name pending, is what's going to allow us to manage this greater connectivity while still sort of being able to set sane routing and security policies on those interactions. And importantly, Beetle is completely backwards compatible with all existing Bluetooth devices. And the reason is that we do this by leveraging the application layer GATT, which is sort of what current devices actually use to interact. Okay, so sort of very high-level view. Beetle runs on the gateway as a background daemon, and it manages all of the Bluetooth connections. So in practice, when I connect my device to a Beetle-enabled gateway, then the connection is going to be owned by this operating system service, the Beetle daemon. It provides networking to both to BLE devices and to the network and applications through sort of the common operating system abstractions like IPC and TCP sockets. And all of this allows us both to route communication between peripherals and to applications and to the internet, and also leverage the richer user interface that we have on gateways compared to most devices in order to sort of sanely set security policies. Okay, so these are the three mechanisms, which I already talked about enough probably. Okay, so the first mechanism which I'll talk the most about is handle address translation. So again, handle address translation is what's going to enable peripherals to talk to each other. And it does this basically by re-exporting services from the peripherals as the gateway's own services. So what this looks like to other peripherals is when they connect to the phone, they'll see whatever attributes at the GATT level that that other peripherals in the PicoNet have exposed as sort of proxied attributes on the gateway itself. So it just sees the phone as having, for example, a heart rate service, even though that's technically on some other device. Yeah.
I'm a little confused.
Okay.
So you told me before that there was this link level thing thing that was basically unidirectional.
Mm-hmm.
Then on top of that goes GATT, and GATT, either person could be a service or
Yeah.
server or a client. And so now you're talking about doing this handle or address translation, but why do I need to do that if both sides are basically just talking GATT?
So the problem that we want to solve with handle address translation is to have communication over two links, right? So we have one link between the heart rate monitor and my gateway device. That speaks GATT. And there's another link between the gateway device and, say, a treadmill. And so right now, there's no way for those two things to communicate.
Okay, so basically you're saying you're just trying to create, here's a two-hop thing that goes back to the host. One's basically advertising GATT services,
Mhm.
and one wants to be a client of those GATT services,
Mhm.
and you're just enabling that connection.
Yeah, yeah. But
So do you actually have to translate the handle someplace?
yeah, so if we,
Not necessarily mutually exclusive, is that the problem?
it's actually fine for them to overlap because they're named by different devices. But so if we only cared about connecting a single peripheral with a single other peripheral, then we could just basically sort of tunnel the traffic over between the gateway device. But in fact, we want to connect multiple peripherals to each other. We want to allow multiple sort of many-to-many communication between peripherals. Does that make sense? Oh.
So maybe the follow-up is the handles that we've been talking about are not unique globally.
Oh, yes, yes.
So that's where the translation is.
Okay.
That's okay.
So I may have two devices connect up. They both use the same handle. I want a client to be able to interoperate with both. Somewhere they've got a map.
Right. Okay. So I didn't repeat the question for the microphone, but what was pointed out is that I neglected to mention that handles are not globally unique. So two devices may both have handle 1, and they will mean totally different things. And so handle address translation is exactly about being able to nonetheless expose both of those attributes to sort of a third peripheral to each other. Is that a fair summary? Okay. Sorry about that. Okay, so right, basically the mechanism is we're going to re-expose these attributes and sort of lift the peripheral handle addresses into a handle address space for the gateway itself. And so that serves sort of a similar role that NAT does in internet connections. So here's an example. I guess I should have used 0200 here. That would have been better to explain that point. So here we have our two devices. We have the heart rate monitor, and that exposes the heart rate service, and a treadmill that, say, exposes like the current cadence or the speed that you're running. They're both going to connect to the gateway, and they're both going to expose each of their services to the phone, to the gateway device. The phone, in turn, is going to take those services and re-export them to the other devices as its own attributes. And importantly, it will use, or it may use different handles for each.
So you said before that things are standardized and what the service means,
Mm-hmm.
and what the actual individual thing means. So, but now you're going to get like the exercise device is going to be a server for the cadence,
Mm-hmm.
and it's going to see another server for the cadence.
Mm-hmm. Sorry, the question was, or the point was that before I said that sort of services are sort of standardized, but now, for example, the treadmill is going to provide the cadence service, but it's also going to see a cadence service that presumably it provides. So first of all, devices don't have to consume the services that they see. That's fine. But more importantly, actually in Beetle, we never re-expose services from one peripheral to the same peripheral again.
Okay.
Yeah. So in practice, and I'll touch on this a little bit later, this is sort of the service export control piece. We don't actually export all services to all peripherals. This is just the mechanism where when we want to expose peripherals to each other, services to different peripherals, then we'll use HAT to do that.
And is it really specified enough that I don't need to know what device it's coming from? Because the advantage of having this, private little connection is that you can go, whisper behind the thing, saying, "Oh, I know what kind of thing you are, and I know how to deal with it." Once you do this advertisement, that service cadence has to be specific enough that everything with service cadence has to do exactly the same thing.
Yeah, so at least the goal of the Bluetooth SIG's service specifications is for it to be specified enough. You know, it's possible for things to expose, like, say, extra characteristics on the same service, and that's not like against the specification. But in principle, it shouldn't break things that don't expect it. Yeah.
But there seems to be an identity problem here. I mean, if there's one person wearing a heart monitor and exercising, and another person wearing a heart monitor sitting and watching TV next by, how does the cadence now the cadence device will see two heart monitors and know who to talk to?
Yeah. So unfortunately, I didn't focus very much on the service export control. That's just one slide at the end. Oh, sorry. I should repeat the question. The question was, the point was that there's potentially an identity problem where if multiple things are connected to the gateway that are exposing the same service, then now, for example, the treadmill might see two heart rate monitors. Which service should it use? So there's two pieces there. Hopefully, if somebody else has a heart rate monitor, it's probably not connected to my. Hopefully, it's not connected to my phone. But suppose it is. The point of the service export control is exactly to expose to the user, to the end user, sort of the ability to say which peripherals should see which other peripherals.
There's a UI component.
There's a UI component. So if you imagine trying to do this right now in a real gym, you'd probably have to hook up your heart rate monitor directly to the treadmill. But if it's not this heart rate monitor, which has a screen, but like one of those bands, I mean, if two people are standing next to each other, how do you even know which one paired to the right treadmill? So the hope is actually that pushing that decision to a richer gateway device that has an LCD screen and a touch screen, and will actually help make that decision easier. Yes.
Is it like something equivalent to ETC services where you define these ports in this service, or is it just private to only this application?
Sorry, can you repeat the question?
On the internet, we have /etc site services. Each port specifying what service is offered. Is it something that handles are standardized for everywhere, or is it application specific?
I'm not sure I totally understand the question, so let me repeat it, and you can correct me. I think the question was whether there's sort of the ability to slice up the services and expose certain services just to a single application.
Or standardized everywhere, it's 0510 means it's specific.
Oh.
No, so I think the question, so the equivalent of we're talking about like SE services and mapping port services is down at L2 cap. We say, oh, this L2 cap channel is GATT. Right? This level now it's entirely name and identifier based. Right? So this is more like the HTTP URL than port API.
Okay. Okay. I'm trying to see how much time I have. That's fine. So right, so that's what this mechanism does. It turns out that it's not entirely trivial to actually do this because of some of the semantics of how devices expect GATT to work. So the first challenge is handle allocation. So while handles are sort of locally named, they don't necessarily mean anything in particular. And in fact, a handle might change between connections. So if I connect to a heart rate monitor, the heart rate monitor service might be at handle 3, and then I disconnect and reconnect, it might appear somewhere else. But the relationship between handles is still semantically important. In particular, groupings of attributes, so for example, a service with a bunch of characteristics, need to be contiguous in the same space. So we can't just sort of randomly stick handles in different places in the space like we would, with NAT, for example, with ports in NAT. And then there's kind of two choices at a high level that you could for how you would allocate handles. The first one is to use one global handle address space. So all peripherals that see a service see it at the same handle. And this is nice because it means that the peripherals would be able to, in the data payloads, exchange handles, and that would still work. Now, as far as we know, there aren't peripherals that do this, but it doesn't seem to. It seems like it'd be nice if that wasn't prevented. And we know that there have been problems, for example, with NAT in the past, which is why we have like UDP hole punching and stuff like that. On the other side, the handle itself might leak some information. Like if I'm some random device that my phone's connecting to, and I see that the handles that I get are very high numbers, that might tell me that the phone has a lot of peripherals connected to it, and that might help me identify who's connecting to me, for example. And secondly, while it's unlikely, it's technically possible to exhaust the address space if I have a ton of things connected and they're all being exposed to each other. Okay, the other option is to have a separate address space for each connection. And so in this case, we lose the ability to exchange handles between peripherals. But on the other hand, it might be more scalable if there's a high degree of connectivity. And we could imagine doing some tricks to sort of allocate handles more efficiently. Okay. Okay, I'm going to try and.
So
oh, sorry. So we ended up using, in our current implementation, we use the global handle address space. Yeah. Technically have a slide on it later, but we're not going to get to it. So thanks for asking the question. Okay, so I'll try and get through these relatively quickly because I don't think I have too much time left. Okay, another issue is discovery. So in the GATT protocol, when I connect to another device, the first thing I'm going to do if I care about consuming any services is I'll basically do a search for those services, and it'll return the attributes that are available. Henry, you have a question?
It's about the last slide.
Oh, sure.
So does the Nike app on my phone specify the handle it wants to read from? Does it actually specify the address, or does it
So I'll use Linux as the example. Android, for example, is a bit more. There's a few more layers of indirection, but typically what you would do is you would say you would basically over your L2CAP connection you would say, hey, tell me about all of the attributes that handle a service of the type heart rate monitor, for example. And what I'll get back is a list of handles. And then for every subsequent operation, like, hey, notify me of changes in the heart rate characteristic, I'm going to use the handle number to name that attribute. Okay, so discovery is hard because basically in this world where the two peripherals aren't connecting directly to each other, they might connect at different times. And when it searches for the services, it might get back an answer saying like, hey, I don't have any services that look like a heart rate monitor. 5 minutes later, I connect my heart rate monitor. What do we do? So that's typically not a problem in a single link communication. But it turns out that some devices will add and remove services. So luckily, the Bluetooth spec has sort of a required mechanism that all devices need to support, which is called the service change characteristic. So if basically a set of characteristics changes in a service, or if a service is added or removed, then the server needs to notify clients that it has changed, and clients need to be able to support sort of researching for those for the services that they care about. So it turns out to not be totally trivial to do this, but I won't get into the details. Finally, notifications is an example of small cases, sort of a small number of cases in the GATT protocol where we actually can't totally transparently just re-export attributes. So the way notifications work is there's one characteristic for a service that will notify for services that can notify me of new data. There's a characteristic that I write either a 1 or a 0 to. 1 turns subscriptions on or notifications on, and 0 turns notifications off. So obviously, if I re-export that naively to a bunch of peripherals, well, one might subscribe to notifications and turn it on, and the other might unsubscribe, and now I've interfered. The devices have interfered with each other. So what do? Well, we just virtualize that characteristic, basically. Okay. Turns out that doing stuff at the GATT layer means that we can actually improve performance beyond what we would be able to do if we were just handing out separate L2CAP connections to each peripheral. And here's a graph showing that. I just don't have too much time. So to summarize, HAT creates a network on top of the Bluetooth Low Energy links by re-exporting attributes from peripherals as the gateway's own services. It allows us to aggregate services from multiple peripherals and re-expose them as sort of one peripheral, which lets peripherals in turn, which only sort of know how to interact with one other thing, actually interact with multiple other peripherals. So the challenge is that we have to maintain the semantics of GATT that applications expect, but it turns out that we can also leverage the knowledge of the application level protocol to retain some of the performance in a way that we couldn't if we were operating at a lower level. Okay, so from the picture that we had before, HAT lets us do this thing, just the interaction between the two peripheral devices. And I will hopefully very quickly, okay, the animation didn't work, but these are supposed to appear all of a sudden. Talk about the next mechanism, which basically enables the rest of the communications. That mechanism is virtual devices. So virtual devices are things that speak the GATT protocol, even though they operate on non-Bluetooth Low Energy links. So it might be processes talking over IPC. It might be some network server talking over the internet. And it could be re-exposing devices through different interconnects completely, like a USB device or a UART or something like that. So that allows us to provide access to non-BLE services. So for example, a phone might expose its GPS as a Bluetooth service to peripherals or to other applications, even though the GPS is not a Bluetooth device. And it allows us to do other cool stuff, like we can emulate a device that either doesn't exist yet or that we're trying to test without having the device actually connected. And we can talk to legacy services over the internet like HTTP services. And so even though virtual devices sort of provides all these things, actually all the complexity is handled by the HAT mechanism. And so virtual devices are actually very, very simple. So I'll talk about the two kinds very briefly, local and network services. So local virtual devices are just user level processes that understand GATT. So in particular, they are going to access Beetle over some sort of IPC channel. On our implementation, which is on Unix, they just speak Unix domain sockets to the Beetle daemon. And they actually turn out to be very, very similar to programming them ends up being very similar to programming a regular Linux app that speaks Bluetooth right now. So what that means is that with sort of very little added complexity, no added complexity really, we can have multiple user applications talking to the same peripherals simply by making them virtual devices. So instead of connecting over L2 cap to a remote peripheral, they'll just connect over IPC to the Bluetooth daemon. But otherwise, it looks the same to them. It's this mechanism that lets us export non-BLE sensors, and as well as sort of prototype hardware. And then finally, if HAT sort of doesn't natively give us the right abstraction for exposing a peripheral to multiple multiple applications or multiple devices, we can actually do this in a virtual device to get sort of more specific peripheral semantics. Okay. Sorry, without losing all of the benefits of being able to speak to it from multiple applications. Okay, and then secondly, there are virtual devices can also be network services. So here there are sort of two scenarios. One of them is where Beetle directly connects over a TCP/IP connection to an internet server that just speaks GATT over TCP/IP. And the benefit there is that we don't have to write a tailored app at all. So even if my gateway, even if there's no app for my Android, for example, that like lets my heart rate monitor store something on a remote server, the operating system itself is going to let the peripheral directly connect to a remote server. And then by actually having a local virtual device that speaks GATT to a peripheral, this lets us support sort of existing legacy internet services like HTTP and REST. Again, without having to have one application completely own that peripheral device. And so this lets us do all of these interactions. You can figure it out for yourself, I suppose. And right, so as I sort of had already mentioned, service export control is important because all of a sudden now we have all of these peripherals and all of these internet services and all of these applications all connected to each other. But in fact, we probably don't want some server like Strava's server to be able to have access to every single one of my peripherals that are on my person or at my home. So we need a way to control who sees what things. And the important part is that routing at the application level protocol actually gives us some more flexibility than we would get by just connecting to things from a lower layer like L2CAP. And so for example, we can actually export only certain services from a peripheral to an external service. So if I have a fitness band that has multiple services, like it has both heart rate and my step counter, I can imagine only exporting the heart rate service to the Strava server, for example. And that's something that I can't do if all I'm aware of is connections. And then secondly, in the case of the Internet of Things, we actually have lots of ways that we might want to do access control and to sort of decide whether to enable communication between two things. And the devices that we're typically talking about, the embedded devices, don't necessarily have a particularly powerful user interface to expose that choice to users. So sort of pushing the authentication from these sort of dumb devices to something like a phone sort of helps us expose these choices to users in a sane way. OK, so to sum up very quickly, Beetle, sort of the thesis with Beetle is that while the gateway should be used to route communication between peripherals and applications and internet services, it should not be used to mediate application data. We do this in Beetle as an operating system service on the gateway using these three mechanisms. And importantly, we do that while retaining complete backwards compatibility with existing devices. And so instead of this horrible picture, we get this. OK, thank you. Yes, question.
So you have all this literature on scatter nets, right? Where one piconet talks to another piconet using relay nodes. You talked about performance briefly. Were you able to compare performance of Beetle with typical scatter nets, which don't use BLE, which use typical Bluetooth nodes?
We haven't compared those two things in particular. Oh, sorry, I turned this off. We have done. We have sort of looked at the performance overhead of, oh, sorry, Laurinus is signaling for me to repeat the question. The question is whether we've compared the performance of doing something like Beetle versus using a typical Bluetooth scatter net. And so this is basically the performance overhead in terms of round trip time of going through something like Beetle versus just connecting directly to each other. So I guess there should be probably another line either here or here, I'm not sure where, that would, that if we were to compare it with typical scatter nets. Yeah.
Imagine extending this setup to multiple gateways, multiple hops. For example, in a gym, my phone needs to see the treadmill, but also the gym's computer wants to see all the treadmills.
Yeah. Yes, definitely. So one example that we've been using as a motivation is, suppose I want to be able to unlock my door, to unlock my Bluetooth-enabled deadbolt with a smartwatch. Well, the smartwatch is connected to my phone. I probably don't want to connect my phone directly to the deadbolt because the deadbolt has to be connected to some other services as well. So I'm probably going to end up routing communication from my smartphone to from my watch to my smartphone, from the phone to some gateway in the home over Wi-Fi or something like that, and then finally from the gateway to the deadbolt. OK, thank you very much.
Thank you again.
Yeah.